Okay. So let's go ahead. I'm just going to start with a bit of review just so we remember where we're at, right? It's been a while since we've been here. So I want to make sure we're on the same page. So we ended off talking about flip-flops and latches. Does anyone remember the difference between a flip-flop and a latch? No one? All right. The latches are not clocked and flip-flops are clocked. Remember that? Okay. So when I draw a flip-flop, what is the name of this device? A D flip-flop, right? And a D flip-flop simply takes whatever is put into the input at the rising edge of the clock and puts it at the output Q with some delay that we call the clock to Q delay. You'll also see me write it as C to Q. Clock to Q. And that just says when the clock edge happens, so the clock is ticking along, this clock edge takes whatever value is on D and puts the output Q, right? Only at the rising edge. So if this is changing a bunch, D doesn't matter, clock only. The D flip-flop, right, is built out of SR latches, multiple SR latches. Now, we have another kind of latch, flip-flop, called the JK flip-flop. This one has two inputs. Now, the behavior of this is such that if they're both 0, then the next time a clock edge happens, we call that Qn plus 1, meaning the next Q. What is the next Q if both J and K are 0? You know?
J and Q are 0?
J and K.
Does it just flip?
Not quite. So on the zeros, we stay the same. Don't do anything. On the ones, we flip. So if J and K are both 0, don't do anything. If J and K are both 1, flip. Toggle is another word for that. Now, in the case of only one of them asserted, only one of them on, right? K functions as your reset, and J functions as your set. So if you assert just K, you reset to 0, you assert J, you set to 1. Otherwise, you retain the same or toggle. Okay. Now, if we were to take these inputs and tie J and K together, it becomes a new type of flip-flop, a different type. Called the T flip-flop or the toggle flip-flop, right? Whose only options are either stay the same or flip, right? It's just, do we tell it to toggle? And then once we had this T flip-flop, I started talking about counters, right? We wanted to start counting with digital logic. And we can do that easily. I'm not sure if I use this exact example of a counter, but we did talk about counters in general last time. Back then, last lecture, I also called them clock dividers, right? Where it slowed it down. These are essentially the same things. because if you remember from the truth table of binary, that you have each ensuing column doesn't toggle, doesn't change until the other one has already done so twice, right? This toggles twice, next column toggles once. So clock dividing is actually the same as counting. Okay, so let's say these are all T flip-flops. And all we have to do in order to count is use the output Q as the input to the next clock. Now, this is actually not quite correct yet. It does count, but we'll get to why it's why I'm going to use Q bar. Now remember, in the flip-flops, I don't have to write that Q bar exists explicitly because we know that it is built out of SR latches. And the SR latch has this kind of structure that gives us access to both Q and Q bar at no extra cost, right? We don't have to add an inverter or anything. We just have Q and Q bar. If we don't want to draw it, we don't have to. But in this case, we want to use Q bar as the clock to the next toggle. The Q then of each of these functions as the counter. Right, and we did essentially this timing diagram last time.
And then all the toggles are
Ah,
hooked high, right?
yes, exactly. And then toggle is always 1. Or we could say another way of saying this is we could call this enable. Right? And that says if the enable is 1, we count. If enable is 0, we don't. Okay. So let's go ahead and use this. And since I've already done the timing diagram on this one, let's turn it in. This isn't what we would call an up counter, right? Because the Q bar here only toggles every time that I get a rising edge of this clock, right? Then since we're feeding into the clock of the second T flip-flop, the second T flip-flop only toggles every other rising edge of the original clock. Okay. But in the case of a down counter, we can change this up a little bit. And instead of using Q bar as our clock feed in, we actually just use Q.
Why was that again? Sorry.
We use Q as the clock for each ensuing T flip-flop. And then I'll draw a timing diagram to illustrate this. Okay, but first off, I have a 3-bit counter. I only have 3 bits. What is in a 3-bit counter 0, 0, 0 minus 1? Right? This is not a signed number. This is an unsigned number. If I start at 0 and I subtract 1, what's my value?
All ones.
Exactly, all ones. Because I essentially have to borrow something that doesn't exist, and so it rolls over. It's the same idea of if I have 1, 1, 1 plus 1, right? So this 1 plus 1 is 0, 1 plus 1 is 0, 1 plus 1 is 0, and I have a 1 as my carry out. But if I don't have a flip-flop assigned to a carry out, it just disappears. So we can go the other way, right? We can go from 0, 0, minus 1 and get to 1, 1, 1. So exactly right. So let's start with, I'm going to call Q0. Well, we'll start with Q0 to 2. All of them are 0. This is a toggle, and I'm saying that, let's say a toggle is just 1, so we don't have to worry about enable or not. And then I go ahead and mark the important locations, which in this case is, where does that clock edge rise? I'm going to use a small but fairly negligible clock to Q delay. It works if you have no clock to Q, but it's difficult to visualize. So I'll use a small clock to Q delay, all right? So this clock happened, this rising edge, causing Q0 to toggle after a small delay. And it's going to do that every time that it sees a rising edge of the clock. So now we have a half-speed clock. Okay. Now, notice it starts at 0. Now let's look at Q1, which also starts at 0. Well, it changes as a response to the rising edge of the 0 T flip-flop, right? This first one. So this rising edge has happened with a small clock to Q delay, which is that orange line. That is where Q1 toggles, but it too has a small clock to Q delay. And then it's going to toggle again way off over here, right? Because I have to wait till the next rising edge of its clock input, which is Q0. Well, Q2 is going to do the same thing, start at 0, respond to the next rising edge, or the first rising edge really, of Q1, because Q1 is the clock for the next T flip-flop, causing it to toggle after a small clock to Q delay. And so what you see now is that after one clock and a small clock to Q delay, I've gone from 0, 0, 0 to 1, 1, 1. Right? I've rolled around. I've counted down from 0. Well, the next step is, if you look at it, 1, 1, 0. Right? That's this. So if this is time 1, this was time 0, this is time 2. At time 2, the most significant bit is still 1. The middle bit is 1, and the least significant bit is 0. So that was just 1, 1, 1 minus 1, which gets us to 1, 1, 0. Right? This is a down counter. Now, this counter and the previous counter are actually what we call asynchronous counters. The reason that this is asynchronous is because the flip-flop, the toggle flip-flop at n+1 is reliant upon the flip-flop at n, right? So if I call this T0, T1, and T2, then we can say that T2 can't toggle unless T1 tells it to. It's not synchronized to the clock, it's synchronized to the previous flip-flop. So it is an asynchronous flip-flop. Or sorry, asynchronous counter. So that's kind of bad, right? Because much like the adder, the ripple carry adder, the larger my counter is, the more number of bits, the slower I have to go. Because you see each bit has this clock to Q delay. And eventually, if I had enough bits, that's going to push the update all the way to the next rising edge of this clock, of the original clock, which means I will never get the correct bit at the very end one before I start updating the next value. Does anyone not know what I mean by that? Everyone's okay with that idea? Okay. So this cascade happens, this cascade of delays, and we can define what is our maximum clock speed. We'll do that in 3610. We won't do that to you yet here. So this is an asynchronous counter. What we want, if we want speed, is called a synchronous counter. Something that is synchronized to just the clock. It doesn't have to wait for the previous bit. Now, as usual, we can fix the problem, right, with a trade-off. So if we want to go faster, we have to spend something else, some other resource. And in this case, it's going to be complexity or size. We add more complicated logic in order to go faster. That's what we're going to do to build a synchronous counter. It's going to be the same idea roughly, but what we're going to do instead is we're going to look at the truth table. I'll come over here and do it this time. And what we're going to say is, what is the pattern? What is the criteria for the toggling to happen? Well, for Q0, it's really just saying that if I'm enabled and the clock happens, so we're going to visualize that each clock cycle is it's going to step from one line of this truth table to the next. So it's time 0, time 1, time 2, right? Divided by clocks. In the case of Q0, it's just if we're enabled and the clock happens, we toggle. So again, the first one stays the same. Well, in this in the next situation for flip-flop 1, T1, we would say that, well, it toggles if the clock hits and Q0 is 1. Right? Each time the Q0 is 1 and we step to the next line, Q1 also toggles. Okay, so the definition for Q0 is just enable. This is when we toggle. For Q1, it's enable and Q0. Well, for Q2, it's enable and Q0 and Q1.
We want to substitute it in, right? Because we don't want to be pulling off the values from the queue, because that will put us back to asynchronous, right?
Yes.
So we have to substitute in the enables, because we have only enables in there.
Well, not quite only enables. What we can do actually here is, you're getting really close to the idea, is what we're going to substitute is, well, I defined Q1 as enable and Q0, which is that, right? So I don't have to necessarily worry about what happens for NQ0. I really just have to worry about enable and Q1. Because otherwise, we're just repeating. This and Q0 has already happened. So let's not worry about it. Okay, so well, what does that mean? Well, we're going to take an AND gate right? Because I'm using the word and, we just translate that directly to the AND gate, and we push that into the toggles. So now we have a shared clock, but we're only toggling if enable is true and this is Q0. So if Q0 is 1 and enabled, the toggle 1 will toggle. Okay, well, this will kind of visually highlight what I was talking about here, where now I'm going to say if Q1 is true and this node. And I call this node alpha. What is alpha? Well, alpha is enable and Q0. So really this Q1 is the result of, well, sorry, I'll call this one beta. Beta is the result of enable and Q0 and Q1. So what we're doing is building up an AND gate tree, right? Yeah, that's what we've built, right? Where the final output of this expression is really Q0 and enable and Q1 and Q2. But each AND gate only has to worry about the output of the previous one. Now, the challenge here is we still do have some delay. It is still synchronous because they're all responding to the same clock. They are synchronized to one clock. It's a synchronous counter.
But at one point, we'll have enough delay to the end, because we have to propagate through all the AND
Yes,
gates.
eventually we will have a speed limit, but that's going to be true on anything. We've just increased the speed limit. Now, my question to you is, why is the clock to Q delay always longer than the delay through one AND gate? I'm telling you it's true, but why? Why is the clock to Q delay always greater than the delay through one AND gate?
So there's more chips in the SR latch, so it has to propagate through more.
Exactly. The SR latch is made out of gates, and each SR latch has 2 gate delays in it, so we end up with 4 gate delays. Yes?
Can you repeat that?
Yeah, we have each each flip-flop is made out of gates, and it is made out of more gates than one. So it's made out of 4, it has 4 gate delays, which means that the flip-flops are going to be 4 times slower than the AND gate. So we've sped it up by like 4 times, or maybe more depending on how the circuit works out, maybe less if you redesign the T flip-flop for some optimal. You can kind of get these flip-flops down to like 2 gate delays, I think. But regardless, we've sped it up. It is now synchronous. You can do a better job with more logic. You can speed it up faster, but that's going to be kind of reserved for the follow-on class to this one, for 3610. Because it starts getting pretty complicated. Okay, so now we can start talking about the VHDL of this, the programming of this type of counter. So what I want is you to understand kind of what you're building when you're writing the code. And part of that is because if you go out and get a job, there is still a chance that you're going to go and someone's going to be like, here's this machine, it's 40 or 50 years old and it broke, I need you to fix it. And you're not going to be the right VHDL for that, you're actually going to have to build counters and stuff. It's within the realm of possibility for some of you that will encounter this type of structure. Now, what's going to happen is you're going to go back and look it up, but I at least want you to have the foundation for what is happening in the digital logic. We like to use VHDL, right? It's just an easier, faster than throwing this on a breadboard or something. Okay. So I'm going to, actually, this is kind of a good question. I know that the translators do, but who of the students actually read the book? A couple of you, okay. That's good. It's a good habit to be into, but I want to highlight some of the things that the book does differently than when I write code, because there's multiple right ways to do it, and I don't want you to get too confused. So for the up counter, we're going to do a 4-bit, we're going to have something that starts with a process, right? Anytime we have something with memory, it's going to need a process on it. Now, if I want to have an asynchronous reset, what signals do I put into the sensitivity list of this process?
Reset and clock.
Yes. Putting reset into the sensitivity list makes it asynchronous. And that's because it can respond to something that isn't the clock, right? That's what asynchronous means, really. As I start out today, I'll try and write good code, and then as we go along, it's going to get more and more abstracted. And we just say something like, if reset is equal to 1, then count gets assigned to 0. Where I'm going to say count is a standard logic vector of 4 bits. Otherwise, else if, so here's where we differ. I would normally write rising edge. They write they say if clock tick event, that's how you would say that out loud, clock tick event, and clock is 1. Well, what does that mean? Well, it's saying the tick event is an intrinsic property to a signal. An event is, did it change? And that includes 0 to 1 or 1 to 0. So they're saying if clock changes and it has changed to 1, so that's rising edge, then do something else, right? I write this as if rising edge of clock, which I will do in a minute, but this works. Now, as far as you guys have learned, does someone see another problem with this code?
The reset isn't 1.
Well, actually, there is a problem with the reset. It does need the apostrophes. But it's actually this. It was what I was looking for. Plus 1, right? We cannot add 1, an integer, to a standard logic vector. Now, the reason that they have this in the book is because the original authors of the book are actually Verilog coders, and they don't do good coding practice. So why this works for them in their sample is they use a library, right? So we use those libraries that are default and then we uncomment. We use IEEE dot numeric standard. The book uses IEEE dot unsigned. Now, the unsigned library does allow you to add an integer to standard logics. Now, I don't let you guys use the unsigned library in my homeworks and on the exams because it is not actually an IEEE library. So IEEE is kind of the Standards Association for Electrical Engineering. They say what is okay and what's not. You don't have to follow it. But what that means is the unsigned library got kind of built onto IEEE just to make things more convenient. But not all technologies will recognize the unsigned library. So if you were to build this code using unsigned at your job, your boss may one day come to you and say, hey, we're switching from the XC7A35 FPGA to the XR12. And you'd be like, okay, cool, I'll just move it over. Well, it turns out that some of those newer FPGAs don't recognize the unsigned library, and this whole thing will just fail. And you have to go back and rewrite all of your code. Whereas if you use numeric standard, as long as you're not using weird Chinese knockoff technologies, you are guaranteed that your code will work regardless of what your final target is. Everyone follow that? Yeah. So this is the right way. This is the book's way, and it's not as good. Okay, so what we do, if we wanted to change this just a little bit, is I would declare count as an internal signal. Instead, it's not a port, it's a signal. And I would declare it as follows. I would say signal count is unsigned 3 down to 0. So it is an unsigned type, because numeric standard does allow me to have unsigned types. And that unsigned type does allow me to add 1 to it. That's pretty useful, right? And then all we have to do is after the process, we do a type conversion. We say Q, right, our output Q, which is also going to be, so Q is going to be a standard logic vector of 4 bits. Now what I say is that Q gets assigned to count with a type conversion. So this, just saying standard logic vector, parentheses count, turns count into a standard logic vector, which is easy because it already knows it has 4 bits. I've added integers to it, and then the output is a standard logic because of this type conversion. That's how I would take with an IEEE standard up counter. Okay. And I would, of course, go in here, and if I'm writing the code, instead of this clock tick event and clock 1, I would just write rising edge of clock. So I just wanted to highlight that because the book is going to do things a little bit differently. They're not entirely wrong, but they're a little bit less right. Like you would get points for it, but not all points, you know? Okay, and now if on this one, I get all the way up to 15, right? 1, 1, 1, 1, it's going to roll over. So it's going to reset to 0 at 15. This counter counts from 0 to 15, so it's 16 values, right? What happens if I want to only count to 11? How would I do that in this code?
Just add a or in the first if.
Yeah, exactly. So if reset is equal to 1, or count is equal to, well, the binary of 11, right? I'd actually have to write out the standard logic vector for that, but if count is, actually, I might be
When
able
we're
to,
converting it, right, so isn't it,
well, I could do Q, but you don't want to access
Yeah.
Q both inside and outside of a process. So I want to use count, which I actually think you can count. Oh,
because it's not, we're converting it, so it's not a
yeah,
standard logic, right?
yeah. So because it's a unsigned, you may actually, I don't know, be able to convert that to compare that to an integer. I don't know. Otherwise, you could just figure out what is 11 in binary, right? And 1, 0, 1, 1001, something like that. Anyways, yeah. So that's all you would do is if I wanted to add reset as a specific value. Now, this is something that I really want to do all the time, in fact, because as I said, digital logic doesn't know time exists. What it knows is clocks exist. So if I have a 1 kilohertz clock, right, which means that I have a clock 1,000, a rising edge of a clock 1,000 times each second. That's what a 1 kilohertz clock means.
Yeah, one more time.
Okay, 1 kilohertz clock means that I have a rising edge 1,000 times per second. That's 1 kilohertz. Okay, so I can't tell my logic to count to 1 second, but I can tell my logic to count to 1,000. And that's how I would wait for 1 second. Is I would say, hey, here's a counter. Every time I get to 1,000, let's assert some output. Let's say, let's call it F. F is equal to 1, and count goes back to 0. So for 1 clock cycle, there's some F that's high, then goes back to 0 as we reset. That's how we would say, hey, I counted to 1,000. I waited 1 second. And then you have to do the math if your clock is faster or slower at different times, right? But that's why we use counters, is we want to wait amounts of time. All right. So I'm going to introduce a new type of device. And we've talked about registers, right? So a register, at its simplest, is just a D flip-flop. And all it means is I'm remembering a value for you, right? I've registered this value. This is the basic building blocks of memory in a computer system. Now, we want to build this into more complicated types of registers. The most common type of register that you will encounter is called a shift register. Well, sorry, the most common type other than a normal register is shift register. And what a shift register does is, well, I'll illustrate it in a little bit, but it just takes a value and kind of passes it down the chain like a game of telephone. I'll give you a visual demonstration of this because it's much easier to see visually than it is to hear it. But what I want to prime you for is why shift registers. Now, shift registers are all over the place. And they handle things like data queuing, meaning you may generate more data than you can process quickly. So what you would do is create a shift register and create a line that says, I'll process you when I get around to it, one at a time. It can also do what we call data conversion, which you'll see as serial in, parallel out, cycle. So an example of this would be something like your mouse on your computer. Now the mouse talks to your computer over serial, meaning it sends 1, 1, or 1, 0 at a time. So it looks like a waveform. So it might be like 1, 0, 1, 0, right? the information that it's sending is really the direction that you move the mouse, right? So you can't just rely on one as useful information because you had more directions than up or down, right? And you also have magnitude. How far did you move it up or down and left or right? So let's say you did the simplest and it just has some update rate that it has 4 bits and it just sends 4 bits. Well, your computer wants to process those 4 bits in parallel. So it's going to have a register of 4 bits that is, each of these bits has some output connected to a circuit. We want to do something with that information that your mouse just sent, right? We want to update where the cursor is. And we don't do that 1 bit at a time, we do that in parallel. But I receive the data 1 at a time. So serial in, parallel out. So at time 0, when we start out, this register is filled with don't cares. I don't care what's in it because it's not ready. Well then, after the first clock, so this is time 0, at time 1, I shift in the first received value. In this case, a 1. But everything else is don't care. At time 2, this 1 gets passed on down the line, like a game of telephone, and it reads in the next thing that came, which is a 0, and has don't cares. Well, continue on, and you'll hear me say clock in the next value. So at the rising edge of the clock, we'll clock in the next value, and we get, and then lastly, after 4 clocks, I finally have, now you'll notice this is in reverse, the way I've written this, right? Because I said I wanted 1 0 1 0, and I got the reverse of that. Basically what happened here is like if you were to declare this as standard logic vector 0 2 3 instead of 3 down 2 0, right? It's not easy, it's not difficult to flip that around if you wanted. It's just easier to illustrate this way. Okay, so now I've shifted it in, and this shift register might have like what we would call a ready flag, and it would just say, hey, I've got 4 bits, take them away and do something. So that would be serial in, parallel out. Now, the reverse is true. If I wanted to send data to something serially, I might want to build a shift register that is parallel in, serial out, PISO. Where I would load in, say, a coordinate and then send it out 1 bit at a time. You will use these a lot in 3610 if you take that class. But it looks the same, right? It's still a register, it's just that it gets a parallel load and then sends them out 1 bit at a time. And then when it's empty, it raises what we would call an empty flag, or just a notification that says, hey, I'm done, load the next one, I'm ready to go. We'll also use these for what we would call sequence generators. So like a simple example is if I wanted to use a shift register to build a slower clock, I could. So I would do something like this. I build a serial in, serial out shift register, SISO. And I would just tie the output back to the input. So it just loops around. And each time the clock happens, it tries to throw this 1 away, but it gets stored back in the first slot. So what happens is each clock, it goes 0 0 1 1, right? And just repeats that over and over again, or this signal output here is your new clock. because it says 1, 1 for 2 clock periods and then 0, 0, right? So you could use a shift register to build a sequence generator or a pattern generator. You just load the pattern in, tie the output back to the input, and it just cycles through that pattern.
And then you could use a shift to build what?
A pattern generator. We do this all the time, actually, as electrical engineers. A big one that you'll hear, I talked about another student about this. You'll see it. This isn't going to be on the test, but I just like to tie it into real stuff. Called PRBS, which is pseudo random bit sequence. So computers are really bad at generating truly random values. So we call them pseudo random, not quite random. And what we want to do is be able to test if a communication system is working. So we build up a test sequence of not quite random bits, and we send them across, and we compare it from the transmitter to receiver to make sure we got all of the data. So that's why, like, an example of why we would use a pattern generator shift register is for test purposes. Okay. So what happens physically for the shift register? Let's go ahead and build one. The easiest way to build a shift register is just DQ flip-flops. So what I'm going to have you guys do is actually do this timing diagram yourself. So I've noticed that students are generally struggling with these still, so I'm going to assign some more timing diagram homework. What I want you to do, and right now get out some paper, draw a timing diagram for 4 clock cycles. So I guess we don't need this 5th one. For Q0 starting at 0, Q1 starts at 0, and Q2 starts at 0. But I want the input, actually let me create a new line right below clock because that makes it a little easier. Input, I'll call that I. I want I to start at 1 and then drop to 0 here. And then Q0, Q1, and Q2 all start at 0. Now, it's a good idea. You don't have to, but it's much easier to comprehend if you give yourselves a small clock to Q delay on each of these. Go ahead and take a moment to finish this timing diagram for 4 clocks. Yes.
You want them to create a timing diagram that starts at 0 and goes through 4 clocks, is that what you said?
Yes. And another way you could just say, finish this timing diagram for 4 clocks. And I can go ahead and I can like mark off, right, the reminder. You want to find the important locations in that timing diagram, which again is just the rising edge of the clock. And my recommendation is don't try and do Q0, Q1, and Q2 in parallel. Do Q0, then Q1, then Q2. Almost done, looks like. All right, so I'm going to go ahead and start this timing diagram. I'm just going to start calling around what happens at the first clock for Q0.
Goes to 1.
It goes to 1, and we're going to give it just a little bit of delay. Because there's a 1 at I, right? The input has a 1, so at the clock, we update the output Q0 with the input, which is 1. What about the second clock?
The second clock is 0.
Yes, it goes back to 0 because the input is now 0. So it's updated again with the new input. And then it's going to stay there because the input stays 0. Okay, Jason, what happens at Q1 on the first clock? Consider what the input is to the second flip-flop.
I think it'll go up with Q1, with like the clock, when they both go up at the same time.
So that's the trick, is notice that the input, and again, I'll just label these as T0, T1, and T2, is that for T1, the input is Q0. We don't care what I is, we care what Q0 is. So what is Q0 at clock 1?
I guess I'm not really clear. If the clock rising edge, so if the clock rising edge comes before Q0, we ignore that for Q1. Is that what you're saying?
We don't ignore it. We update the output with whatever the value of the D flip-flop's input is. In this case, the input for Q1 is 0 at that first clock. So therefore, it just stays 0. Now at the second clock, what is the input to that D flip-flop?
That'll go up.
Yes.
1.
because at second clock, its input, Q0, is 1. So we update it. What about at the third clock? What happens?
It will go down.
Yes. Okay, and now what do we get at Q2 on the first clock?
Stays at 0,
Perfect. Second clock.
still 0,
Third clock.
not goes up to 1,
Perfect. Fourth clock.
not drops.
Drops to 0. Yes, exactly. So this is the shift register. You see this 1 shifting through, right? Stepping through from one to the other, getting passed along. Now you could do a sequence, and I likely will. I will probably give you some sort of diagram like this on the exam that says, given this clock and this input sequence, finish the timing diagram, right? Or it might be a shift register. I might even have, I can do a next one, a parallel load shift register. And I would add a signal that says load.
So this only works because of that gate delay essentially, right?
It actually doesn't. So I'll see if I can draw this in a way that makes sense. The way that I know how to do this, like explain it, it uses calculus, but that's not a prereq to this course, so I'm not really allowed. So if I have a rising edge of a clock right here, well, so this is clock, and I have an input that is high and a Q that is low, and it's going to be updated to high. Good. Maybe I shouldn't even bother erasing this. Maybe I'll modify this one without a delay. So this one changes immediately, right? So then you can have this issue of, well, when that clock hits, that first clock, is the input Q1 equal to 1 or 0, right? That's the issue. Is it 1 or 0? Well, because there is no delay between the updates, it is actually still 0 at that rising edge of the clock. They happen at the same time. So it hasn't, so while the rising edge of the clock has happened, at the instant that the clock hits, it hasn't yet updated to the next value. It hasn't changed, Q0 hasn't gone to 1 yet. The way that you express that, have you taken calculus, right, is you have this delta t idea, and you take t as it goes to 0, and you know that as long as delta t is greater than 0, it's obvious, right, that it isn't updated yet. But you can use convergence to say that, well, it's still true for time equals 0. It converges to the correct update. It doesn't just flash through. It's just hard when you get down to minute timescales, 0 timescales, which is why I do the delay, is because it makes it kind of obvious what it should do. But it does still work even with an ideal circuit. It's just a really wonky math because it can't happen, right? It's not a real situation. Okay, great. That's the shift register. Now I want to build up a parallel load shift register. And I want to start by pointing out, if you recall, because it's good to call back things, right? If I didn't want to shift, I would have a problem, right? Because this is going to shift every time a clock happens, no matter what. It's just whether I'm shifting in data we care about or data we don't. This can be a problem because sometimes your data acquisition device, wherever the data is coming from, gets behind, right? Things slow down because of like temperature changes or just like a glitch that it has to figure out. So think about like if you, I don't know if you're old enough to have like an actual digital camera that isn't part of your phone. And it kind of works on your phone, right? Where you take a picture and the delay between clicking picture and it showing up on your screen and updating is not the same, right? It changes based on what the rest of your phone is doing at the time and what was that picture of. So we want to be able to turn off the update, right? We don't necessarily want to shift on every clock. We want to shift when enabled. Well, the way we do that, right, we talked about the bad way, which is creating a gated clock. Right? Where in order to have clock, I need enable and clock. The issue with that is it's unclear if the enable is a clock or not, right? So for an example, if this clock is ticking along and the enable goes high here, well, what's happened is I go 1 because of that enable. I'm potentially at the wrong times. Actually, I have to do this the other way, right? So we're already 1. And then if the enable, say, is a user input switch, like I want to flick it on, right? It may bounce, right? We talked about bounce before. And so now I get this weird kind of pseudo clock appearing at the output, right? That's why gated clocks are bad, is because it doesn't have any way of differentiating between the clock and enable. It doesn't know which one is actually the clock. So what we did in the previous one is we built a mux, right? Like so. And now what happens is if I'm not enabled, the output just gets passed back to the input and we stay put. That's the right way to keep an enable in a D flip-flop. However, you'll notice if we did that in this one, we needed 1 mux for every single flip-flop. We add complexity pretty quickly. Anyways, let's keep that in mind for just a minute while I move on to how do we do a parallel load flip-flop or shift register, right? So I talked about serial in, parallel out. I want to build a parallel in, serial out. And the way I'm going to do that is I'm going to create some simple logic to address the issue. Give me a moment of drawing and then I'll walk through it. Change the colors on these. Okay, so I'm going to start here. So this circuit, what does this look like? Does anyone recognize this? That's all right. Look it around here. So it's going to have a signal that we call, I'll draw it up here, shift or load, and more specifically, not shift or load. So what that means is that if it's 0, I shift. If it's 1, I load. So I can either shift in or load. Sorry, shift out or load, right? Now, I is our serial input. If they're shifting, it'll just take I. If we're loading, we want to take P. P0, P1, P2. We're going to get to those ones. Okay, now you'll notice that the shift load goes through an inverter to one AND gate and goes directly just into the other AND gate. So the both AND gates cannot be on at the same time. So this is functioning like a select signal, right? It's choosing which AND gate. And the AND gates then are, do I want the input or the parallel load input? Which one? Let's select. The OR gate ties that together and feeds that into data. Well, now we can do essentially the same block over here. And feed that into the D port of the second toggle, where we again know that one of these wants to be tied to, and I'm going to move this over to P1, right? Parallel load 1. And the outputs are tied the same way, the output to the AND gates. And one of them is tied to not shift load, and the other one is tied to the invert of that. Okay, last question then. Where does the other input to this AND gate come from?
The output of the first.
Yes, exactly. The output of the first flip-flop. So now, once again, if I have shift, if I'm telling it to shift, it will take Q, right? And then this is enabled, and pass it through the OR gate and as the input to D. That's how, and then we just repeat the circuit over and over again for each flip-flop. That's how we build a parallel load shift register, right? Is I'm either shifting from Q0 to Q1 and so on, like the previous example, or I can load in P1, P2, etc. Parallel load value. Now let's take this circuit and without adding any components, how can I turn this into an enabled or not enabled shift register? Without adding any components, how can we change this into having an enable signal? It's fine. It's a bit hard to see, but basically, as long as we take Q0, the output, and tie it back into the parallel load, then what happens is our shift or load ends up as an enable. Because if we're shifting, we're shifting. If we're loading, we're just holding the same value that was already there. And in fact, if you really look at this, this is a mux, where the shift load signal is the select signal, and it's choosing one path or the other, and it's taking an output and either taking the next one or holding on to the previous one. So this would be Q1 tied into P1, right? Because then when the clock hits, it just takes, well, whatever Q1 is, we'll pass it to P1. We've selected it, it passed into D, and update Q1 with itself. Not enabled, right? Does everyone get that? Okay. Yeah, that's it. I'm going to call that quits here for today. When we come back, I'll pick up with some, we'll do a quick review of the shift registers. I got a little farther than I anticipated. And then we'll jump into VHDL of shift registers. Thank you. Yeah, have a good day.
I put it in the